Well, this is another short video that is about the spatial memory used in MIPS and stack. So if you don't watch the first video regarding the procedure call and the nested procedure call, please watch it first before watch this video. So, well, as you know that we have a special register in the MIPS register set. It's called the stack pointer. It's register number 29 that is used to address, allocate and deallocate the memory in a stack. So let's move to the registration. So in a stack pointer, first you need to decrement it by 4 to store any value from the register set. So before going to the deep, you need to keep in mind that stack is a memory that is used by the local procedure. So once the local procedure want to use some register, but you don't know while the main function already used or not. In that case, what the local function can do, local function first copy that particular register value to the stack, and after that it can use that register. So once the program finish, then it again load the same value from the stack to the register. To do that, what you have to do, you need to first make the space to the stack, and that is done by this instruction stack pointer. You need to add -4 to reduce, to make the space. If you have to use two variables, then you have to use -8 instead of -4. And then you need to store the corresponding register, for example S0, to the stack pointer. And now you can use the register S0 to your local procedure. Once your local procedure is finished, you save your return type to the corresponding V register, and after that you need to update your corresponding register, and then you need to reduce the value of the stack pointer to go back to the register. Look at the example here. Once you use the callee can be used to the stack pointer by changing the address of the stack pointer, and after that it must be updated. So this is the look of the stack during the procedure call. In principle, here I put the summary in both English and Japanese. So what you have to do, you need to first make a space by decrementing the value of the stack pointer by 4, 8, 12, 16 like this, for using based on the number of variable. And then you can store the register to the stack as you need. After that you can execute the procedure for the register. You can use your register, and after you're using, you restore the original value of the stack, and finally don't forget to deallocate the space from the stack. Have a quick look in this Japanese of the same text here, and now I'm going to move the operation of the stack pointer. So as you know, we have 32 register, and among them we use the particular register. Stack pointer is the 29 number register to handle the memory operation in the stack. As you know, in the function, the early video, I have been discussed that the caller and the callee need to follow a convention for the register. So it's not like that you can freely use the number of register and these. So what you have to follow, where the argument and the result must be stored. You know, you have the register A0 to A3 and V0 to V1 for the result. You cannot override the register used by the callee and the caller. This is why we are using the stack. And if you save the register to the memory or the stack, you must be restore it according to the specification. Because from the callee does not know which register is used by the caller, so what you have to do, you have to store it properly in the stack memory. Well, here's an example. So from the caller main, it called the callee B so it executes the jump and link B. And inside the V, it calls C, so it calls the jump and link to C. And then it's returned to the C, and again it's returned to the B. This is a structure for nested function call. Now we're going to see how we can handle this nested call using all the variables towards our stack. Well, so look at the stack here. This is the stack memory, and before calling the function or procedure B, the main already used these two elements of the stack. After that, the main call B, the procedure B. So now B might need some more. Here, B use another two location for the stack, and while it's using this, it call another procedure C. Well, so now B calls C while the stack is look like this. Well, now C might need another three variable to the stack. So once C finish, it need to jump to the B. It must be restored like this. So the stack returns sum as B because again when it jumps to the B, it goes to the position same as while it called from the main function. So this is the way that a stack handle when the nested function call. Well, look at another example. So this is before calling. So the three space is already used by the main or the caller. So during the function call, it uses this number of position, and after function call, it looks like the same as it when it's called locally. So how can we do this? The first thing, we need to decrement the value of a stack pointer, and then we can register it. And once again, if you need another value, we can decrement the stack pointer and store the value for same and same like this. So after using this, we need to restore the value, and it looks the update the stack pointer to this point so that it can move to the early point towards the stack pointer. Well, so now look at the same program that we did earlier during our video. So in that program, we use perhaps I can have a quick look here. We can use this register, and we use T0, T1, and S1 from the default sum. But here we use the stack to save this thing position. Well, the same program here, different of sum. Now we're using with the stack. The first thing, we need to three variable to store. So we update the stack pointer by -3 to make the 3 position to store to register. Well, now we store S0, T0, and T1 to the stack pointer. So now we can use these 3 registers, S0, T0, and T1, because the original value is already stored to the stack pointer. Well, now we can start using the T0 here. So we can add A0 and A1. That means we are operating F plus G. Similarly, here we are using T1 and this, and we also use the S0. Well, so this register T0, T1, and S0 is changed here, but the early value is stored to our stack pointer. Well, so once we store the value to the return variable V0, now what we have to do, we have to again load the value from the stack pointer to the register. Here we do the same thing. So what we can do, we stack pointer, we load the value from the register after using from the local procedure def of sum. And finally, don't forget to update the stack pointer. Where is it? So we need to add 12 so that now the stack pointer load the address, the same address while we call the def of sum here. Well, this is the way we handle the stack pointer. And finally, we go to the main program with this program. I think this is clear to you. The problem is in the early program, div of sum, we are using the T0, T1, S0 without storing these to a stack. So the problem, if the main function already used these 3 register, then its value will be changed. So this problem can be overcome with using this stack with this way. Well, so before that, so we can understand that how can we go handle this. So here is a set of register we have, not all, but we can see that these two are return type. These are for the argument. Okay, so these S0 register are the callee save register, and we have the stack pointer here. Okay, and look, this temporary register and the caller save register. So if you use this way, then you don't need to store all the register from the memory, from the register to the stack pointer. Well, so now come to the same program again, div of sum. So earlier what we do, earlier we store 3 variable to the stack, but right now we need only 1 variable to store to the stack pointer S0, because I know that T0 and T1 is never used by the caller. So this is my own register. I can easily use it and I can change the value. So I don't need to store it to the, as long as I use the save register, so I must be keep it to the register. Okay, so the T0 and T1 we don't need to store the stack pointer, and we do the same thing here. T0 is add, and then subtract. So after that, once you load the result to the result register V0, after that we can simply restore the value of S0 from the stack pointer, and as I say, don't forget to update this for stack pointer value, because now the stack pointer must be in a position where the same when it is called by the main function. And this is the tree exploitation. Now think about the instrument and you have to solve this quotient. Think a couple of minutes to so that you can do this. The program is changed is that is the return a minus b and is called from the main function here. So if you use some register, you must be save it the stack pointer, and here is the code. What you have to do, you have to fill out this point. Well, I think you already got it. If you don't, then look at this answer here. First, you need to load the argument to the. You can also use load immediate instruction to load these, and here load the result. Okay, so now come to the another instrument 2 that use the compare function to this. Think about how we can do this, and here is the answer for you. Well, have a look on this and see you in the next class.